Hello everybody, let's start off chapter 4. This video will go over sections 4.1 through 4.3, which should be mostly, if not all, review. First of all, water is known as a common solvent. The reason is because, first of all, it's very important and it can dissolve many different substances. It can dissolve mostly polar things, but it can dissolve polar and ionic substances very well, there's a lot of those in our everyday life. And the reason that it's polar is because it's unequal distribution of charge. So we have, remember, the oxygen is more electronegative, so it has a greater pull for the electrons than the hydrogens do, and because it has that bent shape to it, there's more electrons on this side, which makes it a partial negative here. This side of the molecule is partial positive, that makes it a polar molecule.
An ionic solid dissolves in water because of its polar nature. Notice how water molecules become attached to the ions of a sodium chloride crystal in the process called hydration. Positively charged sodium ions attract the partial negative charge of the oxygen in water. A similar attraction occurs between negatively charged chloride ions and the hydrogen atoms, which have a partial positive charge. These interactions loosen the attractions between the ions in the crystal, dislodging them from the crystal. Additional water molecules surround the released ions, insulating them from attraction to other ions.
That was not me, but this just kind of shows the process of how the water molecules separate or will go ahead and make a solid dissolve. So just some memory of some terms here. A solute is something that's a dissolved solvent, water in this case, because it's an aqueous solution. The solvent has to be water. If it's an electrolyte, it is something that when it dissolves, it can conduct electricity. So an ionic substance would do that because it breaks into ions. Another thing that would do that would be an acid, because even though it's a molecule, it breaks into ions. But some molecules, like sugar, don't. They're non-electrolytes because they only break into molecules, no ions at all. Strong electrolytes have a lot of ions, so they conduct current very well, and weak electrolytes don't because they have less ions. Non-electrolytes, no bulbs at all. So here's just some shows about how that would work.
Strong electrolytes dissociate completely to give ions in solution that conduct electrical current. Soluble salts, strong acids, and strong bases act as strong electrolytes in solution. Weak electrolytes dissociate to a small extent to give only a few ions in solution available to conduct electrical current. Weak acids and bases are the most common weak electrolytes. Non-electrolytes are molecular species that do not dissociate into ions in solution. There are no ions available to conduct electrical current. Molecular compounds like alcohols and sugars are examples of non-electrolytes.
All right. So, for chemical reactions, you must know what type of reaction it is, the amount of chemicals present in there. So to know the amount of chemicals present, we have to be able to do some concentration stuff. So a little bit of review here. Molarity is moles per liter of solution. Remember, it's the moles of the solute divided by the liters of solution. The higher the amount of moles per liter, the higher the molarity, or the more concentrated it is. So here's just an example of 3 molar HCl. We have 6 moles of HCl if you had 2 liters of the solution. Let's just do a practice problem with that. Let's say that we were trying to figure out the molarity of a solution like this. We'd go ahead and change the grams to moles. We'd go like this, 500.0 grams of K3PO4. And for every, and there's molar mass is given here, that's grams per 1 mole. And I would get about 2.355, and I carry through with my decimals, or carry through my number in my calculator. That's how many moles. So that means the molarity is going to equal that. Again, dots here representing more numbers in my calculator, PO4, divided by the total volume of the solution, which is 1.50 liters. When I divide that out, I get a magical answer, and it is 1.57 molar. That is the concentration that it would be. So just a basic molarity equation that we've done before. We haven't done it with ions too much, but we'll be doing that shortly. So concentration of ions, in this case, we have a 0.25 molar solution of CaCl2. Since every one CaCl2 breaks into one Ca and two Cl minuses, concentration of the calcium will be the same as the original solution, because I get one calcium for every one unit of CaCl2. The concentration of the chlorides will be twice that, because for every 1 unit of CaCl2, I get 2 chloride ions. So the concentration of those ions will be 0.50 molar. So this is a good check here to try to figure out which one would have the greatest number of ions in it. So take a look at that, press pause, and try to figure out which one would have the most amount of ions in this solution. Alright, I'm going to go ahead and show you how I would figure this out. And I like to work with moles or millimoles. In this case, I'm going to go ahead and use millimoles because when I take a milliliter times molarity, remember molarity is moles over liters. If I take a milliliter times that, the liters cancel out, but I end up with millimoles. So if I do that, I'm just going to look at what I have here. So I have 40 millimoles, 400 times 0.1. Here I have 30 millimoles. Here I have 20 millimoles. And here I have 80 millimoles. So you might say right away, well, obviously you have more sucrose, but we're talking about ions. Sucrose is not an ionic thing, so there's not as much, there's no ions at all. So that is automatically out. So now we've got to take a look at how many ions these are going to break into. All right, this is going to break into, so I have 40 millimoles of the whole NaCl. So it's going to break into one Na and one Cl. So 2 ions it's going to break into. So really, as far as ions go, I'm going to have 80 millimoles of ions. Here I have 1 Ca and 2 Cl, so times 3 ions. That gives me 90 millimoles of ions. And here I have 1 plus 3, so 4 ions, because there's 1 iron and 3 chlorides for every 1 FeCl3. That would give me 80 millimoles of ions. So that means that B here is the winner of how many ions, which one would have the greatest number of ions. So there we go. Alright, solution with the greatest number of ions, not necessarily the one with the largest volume, or the one that has the greatest number of ions, or the one that has the highest molarity. It just kind of depends on which one has the most moles in the end of ions. Dilution is another thing that we did in the past. That's where we added water to a concentrated solution to try to figure out, or to try to just bring down the concentration of something. Does not alter the number of moles of something present. We are simply diluting it and making it the same amount of moles in a larger volume of water. The moles of the solution before equals the moles solute before and after are the same, and that's why we use the formula M1V1 equals M2V2. So here's a good question for you. Which one of these will decrease the concentration of the salt solution? Again, I want you to pause it and just look at it and think about what you think, and once you think you have the right answer, press play. Alright, welcome back. Which one do you think will decrease the concentration of the salt solution? So I have the sodium chloride in an open beaker, and I add water to it. Will that decrease it? I pour some water solution down the drain. I add more sodium chloride. I let it sit out, and at least 2 of the above would decrease it. The correct answer is adding water, because that is just going to reduce the amount of moles per liter. Not going to change the amount of moles, but it's just going to cause a greater volume. The pouring down the drain isn't going to change the molarity at all. Adding more sodium chloride will increase the concentration. Letting it sit out to the open air will let some of the water evaporate, so that will actually increase the concentration because I have the same amount of moles of sodium chloride with now less water. So the only one that would decrease it would be adding water to it. All right, quick little practice problem here. Will be our last slide of this video. And we're just going to use M1V1 equals M2V2. We did this in regular chem. Been a while for some of you. I have 2.00 molar, which is my high concentrated. I want to know what volume of that I would need if I wanted to reduce the molarity to 0.8 and make 150.0 milliliters of it. So I'm just solving algebraically for V1. So I'm going to take 0.8 times 150 and divide it by 2. When I do that, I get 60 milliliters. Looks like I have 3 sig figs everywhere. So I'd go 60.0 milliliters would be the volume of the concentrated stuff that I would need. So that brings us through section 4.3, and we'll be moving on to the next section, which is about precipitation reactions next.